Hi everyone. Today we will cover section 7.4, which is about basic theory of systems of linear differential equations, and 7.5, where we are going to solve constant coefficient systems of linear differential equations. Okay, now let's start the basic theory. In this section, we will learn the theory of systems of linear differential equations. Mainly, we will learn something about the solutions of systems and not how we can find them, but how the solutions look like and their properties. Now, when we say system, remember, we meant more than one equation. So in general, so let's say we have systems like this. X1 derivative, and this can be expressed in terms of some others, x1, x2 till xn, plus maybe a function of t. And the second equation, which is about the derivative of the second function we are looking for, can be expressed again in terms of these. And similarly, so we can go until xn derivative can be written in terms of these. Okay. And remember, in the first section, I gave you two examples. One was predator-prey system, the other was a tank problem. And we saw one of them was nonlinear, the predator-prey one, and the tank problem was a linear problem because we were able to express it in terms of a matrix. And now, mainly in this sections, we will look at linear differential equations. So here we assume that all these equations, like which are telling you like fi's are written in terms of x1 to xn and t. So basically all these functions fi's are linear with respect to x1 to xn. We don't care about t here. So which basically tells us that in linear case, we will be able to write then in linear case, x1 derivative can be written in terms of x1 to xn linearly, which means some coefficients, we can write them. So we will have them like p11t times x1, p12t times x2, and p1n t times xn. So as you can see, I mean, the derivative of the first function we are looking for depends on x1 to xn linearly, plus an additional function of t, let's say g1t. Okay, I'm sorry. And then again, now x2 will depend linearly again. So we will have p21t times x1, p22t times x2, p2nt times xn plus an additional function of this. So we can continue this for the nth derivative. So we can write this linearly in terms of the others. Okay, so in linear case, we will have such kind of equations. But now, actually, we can put them in a matrix form because here our unknowns are x1 to xn. And if you look at, I can write our functions, the unknowns, x1 to xn as a column vector. And if you look at here for the unknowns, again, we have x1 till xn. These are all functions of time, t, you can think, and with their coefficients. T, and plus G1 T, Nt. So we can write these systems of equations in this form. So we put in the matrix form. So basically, I will write all my results considering these. So I don't want to rewrite all these things. So I will just use the following notation. So here, I will call this as my x vector, because this x vector will contain its components are the functions which will solve the systems of equations above. And here, this coefficient matrix determines the system. So I will call this thing as P of t. And then if you look at, then this part, it's a vector of functions. I will denote it with G, okay, of t maybe. Okay, so since all these things depend on t, I will forget them in a couple of minutes. So then this one will be, according to this notation, x1 prime, x1 x prime. So then if you write this, our equation becomes the following: x prime, so it's a vector of functions, is equal to P of t times x plus G. Okay, so I will write all my results considering this. And so basically we will try to solve this equation in the later sections. Okay. So now if you have a linear system of equations, then we can write in matrix form. So I'm just denoting the vectors, the vector of functions and matrix of functions with this form. Okay. Now, here, I want to say a couple of things. So like definition, maybe. Okay. So if here, this G vector, if G vector is equal to the zero vector, then the system is called homogeneous. Okay, so otherwise non-homogeneous. Okay. Okay, and just say this is the first one maybe, and second one, and an initial value problem for this system will be similar to the ones we did before. So, but for each function we are looking for here, xi to x1 to xn, we have to get an initial condition. Maybe let me remind you first what we were doing in just no system case. Let me just write it here. So remember, we had like y prime p of t times y equal to q of t. So if you write this thing as one equation, y prime is equal to minus p of t times y plus q of t. So it's just one equation. So you can think like y is just a 1-by-1 matrix here, and q is like g here because there's only one component. And what we had for initial value problem, we were imposing like at a certain t0, we were giving an initial condition. So altogether, so this was called an initial value problem. So this was IVP. At this time, when we are given a system like this, for each x, we need to give a condition. So like for each one here, like for x1 at a specific point, x2 at the same specific point, we have to give a condition. But if you write this thing as a vector notation, so this is exactly x at t0. So if this is given, okay, so if this is given, just I will just throw some numbers like k1, k2, kn. So altogether, now this is going to be the initial value problem. Okay, so together, this is going to be the initial value problem. Okay. All right. Now, and what is a solution? And so I understand, like, I mean, here, maybe let me add that too. So a vector x, or maybe let's say it is phi t, which is which will basically, I mean, have component functions is a solution if its components, or if the vector as a vector it satisfies the equation. If its components satisfy the equations. So basically what you're going to do, like, I mean, if you take phi and plug into the equation, the matrix equation we have, well, then it will satisfy it. So as you remember, like, I mean, when we from the first order equations, we had not just one solution, we had like many solutions. So then if you don't impose any condition, of course, so we will write them as in the vector notation. So now let me say something about their existence And then after this, basically, we will focus on the homogeneous case. So existence and uniqueness theorem. How do we know we have solutions, or when do we know we have solutions? Actually, things are similar to the first order case we wrote. So existence and uniqueness. Okay. So let's say we are given a matrix equation. With initial condition. Let's say this is the first. So this IVP. Now, if you look at the case for the first order case, I mean, like if you remember now this case. So for the linear equation, we said that if P function and Q function here were continuous on an interval containing T0, then we had a unique solution. Things are similar here, but we have more functions. So here, then P must be continuous on an interval. G must be continuous on an interval. On which interval? On an interval containing T0. Okay, but P is a matrix of functions. G is a vector of functions. So that means there are many functions. If all of them are continuous on an interval containing T0, then we will have a unique solution. So remember, like if you look at P means all these functions here. Okay, so we have all these things. They must be continuous. Similarly, all these things. So P is replacing the P function here, like G is replacing the Q function there. So that's the reason now if PT, which means all PIJT and GT, which means all GKT, all the components, are continuous on an interval I, let me say like this is alpha beta interval containing T0, then this IVP has a unique solution, on all I, just as similar to the first order case with not system, just one equation. Okay, so if all these coefficient functions, Pij's, and the functions in the G vector are continuous on a common interval containing T0, on that interval, you will have a unique solution to this IVP. Okay, now, starting from now on, I will focus on the homogeneous equation. And you will see, like for the rest of the chapters until the last one, basically we will focus on the homogeneous equation, and there is a good reason for that. Okay, now consider, so I'm just writing it with colorful letters. Okay, so consider X prime P of t times x. Okay, now until the part where I'm just going to state the non-homogeneous one, we all consider the homogeneous. So homogeneous. All right. Now we will state the first thing about this theorem. If x1, I'm sorry, okay. If x1 t, at least for this one, let me write what is x1 t. So this is a vector of function. So I will write its components as x11 t, x21 t, xn1 t, and x2t, which is x12t, x22t, xn are solutions to x prime p of t times x, then their linear combination, which means like C1 x1t plus C2 x2t is a solution too, is also a solution. Its proof is very easy. Let's do it. Proof. So take their combination and plug into the equation, see whether it satisfies or not. Okay, so I'm taking the derivative of this. So derivative is, so you know the rules of the derivative. So taking the derivative means basically taking the derivative of x1 and x2 because C1 and C2 are constant. C1 x1 prime plus C2 x2 prime. Now x1 is a solution, so it will satisfy. So I can replace x1 prime with p of t times x1 because it satisfies the equation. Similarly, second one satisfies the equation. Okay, so I'm replacing with that. But now p of t is common, so I can take p of t parentheses. Okay, so what do I get? C1 times x1, C2 times x2. So as you can see, I have a vector of function here. Vector of functions here. Its derivative is equal to p of t times itself. So which basically satisfies my equation. Derivative must be equal to p times itself. So this is the linear combination. Okay, so this means I can find then if I have some more equations, I can take their linear combination. If I can do for 2, I can do for all of them. So if you have tons of equations, take their linear equations. So these are the linear combinations, then it will satisfy. But how many do I need? I mean, will I write all of them? Will I take the linear combination of all of them? Of course not. Of course not. Now remember, like from maybe physics. So when you take in like R2, remember, if you take any vector, then any vector can be written in the form A times I, B times J. So which means that if you take linear combination of I and J, then you can write any vector. So if you have we will have lots of solutions. Then will I need all of them to write the solutions? Of course not. So if we can find some solutions doing the job like I and J, then we will be able to write all solutions as a linear combination of these. Okay, so just a note here. Then basically the following result says this. But before this, I mean, let me just do a couple of things and remind you something about linear independence. So let's say that we have x1, xn be solutions, be n solutions to our homogeneous equation x prime p of t times x. Now, they will have components, so we can put them in the matrix form. So let's consider the following. Let's consider, let me call this thing like x at this point, but later I will call it with a different letter. So x11 till xn1. So we basically, the first column is the first solution. Second column, I'm sorry, 1, 2. Okay, let me. 1, 2. This is your second solution. And your end solution is the last one. So 1n. This is the end solution. Now, recall that, I mean, so if I take their determinant of x of t, and if this determinant is not 0, if this determinant is not 0, if for any given t, then x1 till xn are linearly independent for that value of t. Okay. Now, I want to say one thing here. Remember the linear independence. So just these are like functions. These are not numbers. You put t here, t and t. Okay. So for any value t, if this determinant is non-zero, automatically they are linearly independent. So if so let's not confuse the following. So being linearly independent on an interval. So remember, how for a vector of functions, how do we check being linearly independent on an interval? Basically, we were doing the following. So we were taking their linear combination, we were equating to 0. And if if we get all C1 to Cn equal to 0, then we were saying they were linearly independent. And we had a determinant condition. If the determinant is non-zero, at least at a point on an interval, then we were saying, yes, they are linearly independent on this interval. But if the determinant is completely zero, as we did in an example, this doesn't mean they were linearly dependent on the given interval. Okay, but now here, be careful. I'm just saying for a specific value of t, I'm checking whether they are linearly independent or not for all t on an interval. I didn't mention anything about an interval here. Just for a specific point of t. If this determinant is non-zero, automatically, then they are going to be linearly independent. Of course, I mean, on an interval, if for each value of t, this determinant is non-zero, you can directly say, yes, they are going to be linearly independent on the interval. Even like if it is non-zero, at least for a point on the interval, automatically you can say still they are going to be linearly independent. But here I'm checking point by point. Okay, for that value of t, they are going to be linearly independent. This is basically what we are going to assume, or we are going to ask basically in our solutions. For each value of t, they are going to be linearly independent. Okay, so for this value of t, we said they are going to be linearly independent. So that's the reason this can be written as an if and only if statement. I mean, like if for any value of t, this determinant is if and only if, basically, if the determinant is non-zero for the value of t, that means if and only if they are going to be linearly independent for that value of t. All right. So this determinant has an A. So here I took n many solutions, I put them in a matrix form, I compute their Wronskian. That's what we are going to call. Okay, this determinant name is called Wronskian. So here, determinant of x of t, which is determinant of these. Let me just write maybe the following way. First, determinant x1 till xn1 x1n xnn. Okay, so this is written as Wronskian, or sometimes Wronskian determinant. I'm sorry, we're putting the index above. So okay, so we are basically computing the Wronskian. Okay, this is called Wronskian. Okay, so if the Wronskian of n many solutions is not zero, then at that point they are going to be linearly independent. So also, if they are linearly independent, then Wronskian is not zero there. Okay, so because we are doing point by point, let me just rewrite it. So x x1 to xn, these are the solutions, are linearly independent at a point, not on an interval I'm talking about here, be careful, if and only if their Wronskian correct these. These are. So be careful. I didn't write t inside because I'm talking about at a point that means that t value is not 0 there. Not 0 there. Okay. So now we have n many solutions. We write them in a matrix form, and we check the determinant, which is called Wronskian. If Wronskian is not 0 at a t value, for that t value, they are going to be linearly independent. Of course, on an interval, if it is true for all t value, then it's going to be linearly independent on that interval. All right, now let's come to the theorem. So if x1 to xn are linearly independent solutions of our homogeneous system, okay, for each point in the interval then any solution phi of the system can be written as a linear combination of these solutions. Can be written as C1 x1 to Cn xn. So it can be written as a linear combination of these. Okay. So let's prove this, and after this we will say a couple of things. Be careful now here. For each point in the interval, for each point in the interval, we have linear independence, which means basically the Wronskian of these functions, of the vector of functions, are not 0. Okay. Now, proof. Let just choose any t0. Let t0 be an element of alpha beta. Okay. So and now let's evaluate the solution phi at t0. And let's say that this will be for each, of course, for each component, it will be evaluated. And let's say this is phi1 t0, like this, phi n t0. So we will get some numbers here. Okay. Let me use again like this way, k1, k2 till kn. Then now, Then now, let's consider the following system. Consider the following system. C1, X1 at T0, Cn, Xn at T0 equal to phi at T0. Now, for this T0, we know that all the vectors I wrote here, X1 T0 to Xn T0, they are going to be linearly independent. So which means that, we have the following basically system. Cn. So this is X11 T0, T Xn1 T0, X1n T0, Xnn T0 equal to this K1, K2 till Kn. Okay, this is what we have. And now if you look at this matrix is determinant is going to be non-zero because we know that they are linearly independent for each interval. So this matrix is determinant is non-zero, which says that it's an invertible matrix, which says that then you can solve this problem uniquely. So you can find C1 to Cn, can find unique C1 to Cn, which will satisfy this thing. So now we can find this and we can solve it. All right. So let me just rewrite this part. So this is equal to the Wronskian of X1 till Xn at T0. And we know from linear independence for each point, this is not zero. So we have a unique solution here. Okay, we have a unique solution because this matrix is going to be invertible and you can easily find C1 to Cn. So then now let's look at the two solutions here. One of them is for this C1 to Cn, I am taking the following combination. So both of them, like these C1 to Cn are determined by the above equation, are solutions to x prime p of t x, and they satisfy the same. Let me just say this is like x here, and x t0. Sorry, erase this. X t0 is equal to phi t0. So if I give the initial condition at t0 as k1 to kn, phi satisfies this, and this x satisfies this. So we know from the uniqueness of the initial value problem, then if x t0 and phi t0 are equal, and if both of them are solutions, then they must be same. By uniqueness of IVP at t equal to t0, 0, then x, which is equal to c1 to cn now, must be equal to phi of t. So which means now I was able to write the phi any solution in terms of this x1 to xn. Okay, then here, which means that if you know n many solutions, then you can write any solution by using them, as long as they are linearly independent at each point in an interval. So then we can say the following things as definitions. Here, according to this, x1, c1, cn, this is called the general solution. So this is for arbitrary C1 to Cn, for arbitrary C1 to Cn, this is called general solution. General solution. If their Wronskian is not 0, which means they are linearly independent. Wronskian is not 0 for each t in the interval. Alpha, beta. And we say like and we say this set like x1 to xn is a fundamental set of solutions, and it's a fundamental set of solutions. So then what does this thing say? You are given a homogeneous equation and you want to find the general solution. Then you need to find n many solutions which are going to be linearly independent for each point in the interval I. Which, how can you check this? The Wronskian, which is the determinant of these solutions, must be non-zero for each point in the interval. Then we call this thing general solution. And as a set, if you write them, x1 to xn, we call this a fundamental set of solutions. Maybe furthermore, the matrix is called a fundamental matrix. Let me just state it at this point. So x1, 1t, x and 1t this matrix PC is called a fundamental matrix. I'm saying a fundamental matrix because you can write tons of fundamental matrices, as long as you find n many solutions which are linearly independent, you can form a matrix, and that matrix is going to be called a fundamental matrix. Okay, so the matrix we have this. So how do we know like we can find n many solutions, by the way? So let me just say this, not right maybe. So you can produce, by using the existence and uniqueness theorem, you can find n many solutions actually. So just impose n many initial conditions at a given point. So let's say like at t0, your initial condition is 1, 0, 0, 0, 0, like this. And then, or at t0, it is 0, 1, 0, 0, 0, 0. It goes like this. So you have n different initial conditions. And different initial conditions. So then, but then you can solve this. Theoretically, you can solve it, and the solution is unique. Now you got n many solutions. They at the given t0, each one satisfy different conditions, different initial conditions. Now, if you put them in a matrix form and evaluate their determinant at t0, you will get 1, because at t0 you basically form an identity matrix, and then which means that these solutions are linearly independent at t0. At one point, the determinant is non-zero, but an interval containing t0, then they are going to be linearly independent. So that is on that interval, you will be able to get n many solutions theoretically, and which are going to be linearly independent. So you get a fundamental matrix, or you get a fundamental set of solutions, or then you can write the general solution. Okay. Now, we have the following theorem. I will not prove this thing, but this is just an exercise in the same section, so you can do it. So what does this theorem say? Actually, it's a strong result. Okay, so this thing says the following: if x1, xn are solutions to x prime p of t x on the interval alpha beta, which means, because I mean, like on this interval, now we have these solutions. Now, let me say maybe the result first. Then in this interval, the Wronskian either is identically 0 or never vanishes. So this means like the following. I mean, so you have a system, a homogeneous system, and you found your solutions, and which are I'm not saying anything about the linear independent. You found n many solutions on an interval. These are solutions. Now you are checking the Wronskian, and it says that either the Wronskian is 0, completely 0 on this interval, or it never vanishes. This is a very strong result, and it's basically coming from the following. This is also that you can call this thing an Abel's theorem, and maybe let me state it. this is from the exercises, just basically the Abel's result says the following. So we know Wronskian is a function because you are getting a determinant, so it's a function. So it basically, Wronskian satisfies, the Wronskian satisfy the following differential equation. Its derivative is equal to P11T plus P22, maybe let me just write this way, so the rights may mean everything. P22T, P33T, till PNNT. So I'm taking the trace. Trace is the sum of diagonal entries times this. And from this, Abel's result says that. So if you look at like derivative is equal to a function times W. So W is the Wronskian. So this is a separable thing. So you can solve it easily. So which says that Wronskian is a constant times e to the integral of P11T till PNNT dt. Okay, so which says basically the following. So Wronskian is an exponential times a constant. So if the constant is not zero, it's never zero. If the constant is zero, it is completely zero. So that means for Wronskian, these are the possibilities. All zero, everything is zero, or non-zero on an interval. This is called, by the way, Abel's theorem. So, or Abel's formula. Let me write this. This is Abel's formula. Norwegian mathematician, Abel. So we have Abel's formula, so which says everything. So this is an exercise in the book, so you can do by yourself. So from this, we conclude that if you have solutions of the homogeneous equation on an interval, then it either you get the Wronskian is either identically zero or it never vanishes on this thing. All right. So how about the non-homogeneous case? Let me say for the non-homogeneous case, and then finish the first part of the lecture. Okay, so now we have the following thing for this result, and which basically tells us everything. Now, if y1 and y2 are solutions to a non-homogeneous equation, okay, so here GT is not zero, so it's non-homogeneous. Then their difference is a solution to the corresponding homogeneous, which means I'm just erasing G. That's wait. Okay, so its proof is again very short. Let's do it. So let's take their difference and derivative of them. So maybe at least for the first one, not just write this way. Okay, I'm taking their difference and then derivative. So we get the derivative of the first one minus the derivative of the second one. But did y1 and y2 satisfy the equation, the non-homogeneous equation above? So which tells me I can replace the derivative of y1 with p of t times y1 plus g minus, I can replace this y2 again, p of t times y2 plus g. Now, if you take their difference, as you can see, g's are going to be canceled and p will be common for both of them. So I can write p of t times y1 minus y2. So as you can see, the difference derivative is equal to p times itself, which says it's a homogeneous solution. So what do we learn from this now? We learned the following. So then if we know the general solution of the homogeneous equation, and if xg is equal to c1 x1t cn t is the general solution of x prime is equal to p of t times x, sorry, no derivative. Then this difference can be written by using these Eqns for some C1 to Cn. Uniquely, you can write this, which says the following. What it says the following. So y1 can be written as C1 x1 Cn xn plus y2. So which says the following now. Any non-homogeneous solution like y1 can be written as a sum of homogeneous solution and a non-homogeneous solution. So any non-homogeneous solution can be written as a sum of a homogeneous solution plus a non-homogeneous solution. So if I knew y2, just one non-homogeneous solution, if I add a homogeneous solution to this, then I will get a non-homogeneous solution. So this way, I can get all the non-homogeneous solutions if I know one non-homogeneous solution and all homogeneous solutions, or just the and many linearly independent homogeneous solutions. So this tells us the following. You can write the general solution of the non-homogeneous system in the following way. So for a non-homogeneous system x prime p of t times x plus g. The general solution is equal to C1 x1 Cn xn plus y, let me call this thing yp. Where? So this is, let me just say, this is called the homogeneous solution. And this is called particular solution. Okay. So particular solution. So in other words, this here, this just one solution, one particular solution, which means, so here, if you take the derivative of this, you get p of t times plus g. So that's what you need to do. You just need to find one solution which satisfies the non-homogeneous, and this part is the general solution to homogeneous equation. So when you are given a non-homogeneous system, then what you're going to do, if you want to get the general solution of this, first of all, you will find the general solution of the homogeneous system, corresponding homogeneous system. By just erasing G, you are solving the homogeneous system. Okay, you are solving the homogeneous system, you get its solution. It's the general solution of the homogeneous system, or you can say it's the homogeneous solution. And then you just need to find one solution which will satisfy the non-homogeneous system. Just one solution, one vector of solutions you need to find. So when you find it, when you add them up, you get the general solution of the non-homogeneous. So that's the reason the crucial part to compute the general solution of non-homogeneous is, again, solving the homogeneous, because you need to solve the corresponding homogeneous system to write the general solution of the non-homogeneous. So that's the reason until the last section, basically, we will work on how to solve homogeneous systems. And then in the last section of this chapter, we will learn a method to find a particular solution for a given non-homogeneous system. Okay, so this is the end of 7.4, where we studied basic theory of system of linear equations. And now we will start 7.5, where we will learn how to solve constant coefficient equations, system of equations. Okay, now we will start section 7.5, where we are going to solve homogeneous linear systems with constant coefficients. In 7.4, we learned how the solutions of systems look like. When do we call a set of solutions as fundamental set of solutions? So when do we say they are linearly independent, vice versa? Now we will honestly start solving equations. The first case and the main case, basically, we will solve homogeneous with linear systems, and they are going to be constant coefficients. So what do you mean by homogeneous? Our systems were in the form x prime p of t times x. So, and this was the homogeneous form. I mean, you don't need to put an arrow, so we understand they are vector of functions. So we mean constant coefficient mean. Here, this matrix p of t has entries which are constant rather than functions. Okay, so then how do we get these things? I mean, like they are of the form, like we have x1 prime, a11, x1, so it goes like this, a1n, xn, and we have xn prime, an1, x1, ann, xn. So if you write this thing in the matrix form, and we get here x1 till xn, these are the ones we are looking for. Their derivative is equal to, if you look at the coefficient matrix, now it's going to be a constant matrix. Okay, so x1 to xn. So then if you use, as we did before, this is going to be our x prime, and this is our x, and this is the matrix now I will call as A. Okay, so our system is x prime is equal to A times x. So now what can we say about its solutions? So remember, I mean, existence and uniqueness theorem, everything depends on the coefficient functions. And here our coefficients are constants, which means basically they are constant functions, and constant functions are continuous everywhere. As a result, since they are continuous everywhere, you can just take any initial value problem and we will have a unique solution for it, because these functions are continuous everywhere. Their domain is everywhere, all real numbers. Okay, now how are we going to solve? Actually, there is a general method for solving these things, but at this point, we will just start with certain trials, and then at the end, we will reach a method to find the solutions. And you will see the general theory later. Okay, let's start with an easy example. Okay, now let's consider the following problem. So x1 prime is equal to 2 times x1, and x2 prime is equal to minus x2. So if you write this thing in the matrix way, then this is x1, x2 prime. What is the coefficient matrix now? So the coefficient is like for the one is 2 and 0, for the bottom one, 0 and minus 1. So this is our A in this case. Okay, A. So now, actually, this is a very simple example because we can solve it easily. So if you look at the first equation, it says that derivative of x1 is equal to 2 times itself. And you remember these things from first order case. If you want, you can separate it and you can easily solve. This is going to be an exponential function whose exponent will be 2t. So we can now find x1 is, sorry, it's going to be exponent e to the 2t because its derivative is 2 times itself. Not only this, any multiple of this will satisfy it. So C1 I'm taking. Similarly, if you look at the second one, x2, so again, its derivative is negative times itself. So it's again going to be an exponential function. But where this time, exponent is going to be negative. So its derivative, if you take, it's negative times itself. And not only this, also, I mean, any multiple of this. So I'm just taking any multiple of this. So as you can see, like we were able to find it. So if you look at the solution in the vector way, x1, x2, then c1 e to the 2t, c2 e to the minus t. But I can write this thing in the following way. c1 e to the 2t times 1, 0 plus c2 e to the negative t times 0, 1. So now, as you can see now here, so we are seeing linear combination of these two solutions actually here. So that means this is the first one is the first one in the red box is a solution, because any combination is a solution, because we were able to write solutions in this way. So this, I can take this thing as my first solution. Okay, and the second one again is going to be a solution. So I can take this thing as my second solution. So that means actually, so we were able to write all the solutions C1 x1t plus C2 x2t. Now, so that means probably this is going to be general solution, but to check whether it's a general solution, I need to check the Wronskian. So let's check the Wronskian now here. Wronskian of x1. I'm sorry. So let me just put t out. And x2 t. This is, as you know, the determinant of these things. So if you write these solutions, we have e to the 2t, 0. This is the first solution. 0 e to the minus t. If you take this determinant, it's going to be e to the t, which is never 0. So for any value of t, this determinant is not 0. So for any other value of t, they are going to be linearly independent. So that's the reason I can call this as my general solution. Okay, this is the general solution. So now this gives us an intuition for how the solutions look like. Maybe we can try that one. What is that intuition? If you look at this first solution and second solution, they're in the following form. There's an exponential and there's a vector. Why not? Let's try this. Okay, let's try this for the general case. Now, let's try x e to the lambda t times a vector c for a system x prime is equal to x. So do we always have this kind of solutions, or maybe when do we have this kind of solution? Under which restrictions we have these kind of things? Okay, so maybe it's just a coincidence. I mean, like they are of this form. So let's say we are given any system like this, x prime is equal to a times x, and I'm going to try just a vector of functions e to the lambda t times c, where c is a vector of the same size as x, and e to the lambda t is just your you can think like coefficient, which is a function. Okay, so if it's going to satisfy the system, then its derivative e to the lambda t times c's derivative must be equal to a times e to the lambda t times Coeff. So it must satisfy this. Now, here Coeff is a vector, so it's a constant vector. So its components are constant. So taking the derivative means basically just taking the derivative of the coefficient here, e to the lambda t. Its derivative is lambda e to the lambda t, so times now Coeff. On the other side, we have this. So here, e to the lambda t is just a constant, scalar, if you think. So you can move it anywhere you like. So this is the same thing as e to the lambda t times a times Coeff. So we want this equality to be satisfied for our trial to be a solution. So now let's take everything to one side. Okay. So then we get the following equation. So e to the lambda t a times Coeff minus lambda e to the lambda t Coeff is equal to 0. But be careful, this is 0 vector. Now I can take e to the lambda t parentheses from left, and I want to take Coeff parentheses from right. But again, this is not possible because we have a matrix A here. On the other side, for this part, there is no matrix. So I need to introduce a matrix here so I can do this thing. So I'm introducing just the identity matrix here. So I can take the parentheses of from right and from left. So then if you look at, this is going to be e to the lambda t is common. So I'm taking its parentheses. And then here Coeff is common. So a minus lambda times identity Coeff. This is what we get. Now we want this. So e to the lambda t is just a scalar. So, and which is never 0. So for this thing to be 0, the 0 vector, so then which tells us the following. This thing says that a minus lambda I times Coeff is going to be 0. So if you want e to the lambda t times Coeff to be a solution for x prime is equal to a times x, then this equation must be satisfied. But you remember this equation from somewhere. This is exactly the eigenvalue eigenvector equation. So for this thing, for x to be a solution, it says that your lambda must be an eigenvalue and your Coeff must be an eigenvector. So whenever you get this, you will be able to find a solution out of this. So that means then, if I'm given a system, then I can look for a constant coefficient system. I can look for eigenvalues and eigenvectors. This way I will be able to get solutions. All right. So now let's try this on an example. Okay. Let's look at the following problem. x1 prime, x2 prime. x1 prime is equal to x1 plus x2. And x2 prime is equal to 4x1 plus x2. Okay. And let's give an initial condition. So we want x1 at 0 to be 1. And let's say x2 at 0 is also equal to 1. We will try to solve this. Now, if you write this thing in the matrix notation, then we get x1, x2 prime is equal to 1, 1, 4, 1 times x1, x2, and x1, x2 at 0 is going to be equal to 1, 1. Okay, so we need to solve this. Okay, then from the motivation above, and I'm going to find the eigenvalues and eigenvectors of this matrix A here. So here, this is our A. Okay. Now, how do we find this? We compute the, first of all, determinant of A minus lambda I, which is determinant of 1 minus lambda, 1 for 1 minus lambda. Remember, I told you a quick method for this. For 2 by 2 case, it's a 2 by 2 example. So this is going to be lambda square minus the trace. Trace is the sum of the diagonal entries. So here, these are your diagonal entries. I'm going to add them. So 1 plus 1 times lambda plus the determinant of the matrix A, which is 1 times 1 minus 4 times 1. So which is going to be lambda square minus 2 lambda. So if you do this computation, we get -3. So this is our characteristic polynomial. So if you make it equal to 0, then this is lambda minus 3, lambda plus 1, and equal to 0. So I use the following notation. So what are the eigenvalues then? Sigma A. The eigenvalues are 3 and -1. So now let's try to find the eigenvectors for these. Lambda is equal to 3. Then I need to solve A minus 3 times identity times, because C is equal to 0. So which is basically, if you subtract 3, so we get -2, 1, 4, -2 times C1, C2 is equal to 0, 0. Remember now, again, it's a 2 by 2 case. It's easy to handle. So there was a quick method for this. Now remember, so if you look at, I can do row reduction here. If you take the first row, multiply with 2, and add to the second one, automatically you delete the second row. So they all become 0, 0. So it means you just get basically, there's only one equation here. That's the first equation. And then how are we finding an eigenvector? We were just focusing on the following thing. We were, maybe let me just do the row reduction. So then row reduction gives us the following: -2, 1, 0, 0. So what is the row reduction here? It is 2 times R1 added to R2. And so when you multiply like this, you want to get 0, 0. So as I told you, I mean, it's all about finding C1 and C2. Actually, when you take the product with -2 and 1. So, and we thought this, like this is like a perpendicular vector or orthogonal vector to -2, 1. And how are we finding it? I mean, you just switch the place of -2 and 1, and so and then you negate one of them. So if you do this, C1 and C2, then I can take the following vector as an eigenvector. But we know that not only this, any multiple of this one is going to be an eigenvector. So I'm just taking, like, writing here k times this. Or if you use the free variable, where here free variable is going to be the second one, you don't need to write k here. You can write or C2. Just if you want to use that one, maybe let's write that way. C2. Okay. So this is the vector. All right. 1, 2 is an eigenvector. Any multiple of this is an eigenvector. This is what we got. So if you don't believe, just multiple. I mean, take your dot product. Take the dot product of -2 and 1. So just let's do it for you. -2, 1, and 1, 2. You exactly get 0. So wait, that's the reason, like here it's like taking that product and you are finding a perpendicular vector to -2, 1. So from this, Yes, now I can write a solution. I can write my first solution. My first solution is going to be e to the 3t times the eigenvector, which is going to be 1, 2. So if you want, you can write this is e to the 3t 2 times e to the 3t. Now, we found one solution, but we need another one. As you remember, if you want to write the general solution, you need n many linearly independent solutions. Here, n is equal to 2, so we will need 2 linearly independent solutions. So we have another eigenvalue, which is -1. So I need to solve a -1 times identity, because C is equal to 0. So if you now do this, our matrix is going to be, basically you're adding 1. So we have now 2, 1, 4, 2, C1 and C2 equal to 0, 0. We need to solve those. Again, you can do row reduction. I mean, but I will not do this time. I will just directly write it. So 2, 1, 4, 2. If you take the first row, multiply with -2 and add to the second one, second row will be completely 0, 0. So that means you are now, it's all about the first equation, 2 and 1. So I'm looking for a vector, C1, C2, which is perpendicular to 2, 1. Again, switch the places and then negate one of them. So this gives me C1, C2. Now, what do you want? Switch the places. Like I'm thinking like 4, 2, 1. I'm thinking like 2, 1 as my vector. Now I'm switching the places. So one goes above. And then I negate one of them. So I'm negating one of them. This is what we get. So again, I can take any multiple of this. So here again, if you do the row reduction, your pivot is going to be 2. Your second variable is 3. So that's the reason we get this. So as a result, now I can write my second solution. My second solution is going to be e to the -t, because my eigenvalue is -1, times this eigenvector, which is going to be 1 and 2 -2. Okay, so if you write this, e to the -t, -2 times e to the -t. Now let's check the Wronskian determinant. Let me just write this way. Wronskian of x1, x2. So this is the determinant. So what was our first solution? E to the 3t, 2 times e to the 3t, and e to the -t minus 2 times e to the -t. So if you compute this determinant, so as you can see, we get -4 e to the 2t. Okay, which is never 0. So hence, x1 and x2 are linearly independent. x2, t are linearly independent for all t. Okay, and so that means then I can use them to write my general solution, which is going to be C1, 2, which is going to be C1 times e to the 3t, 2 e to the 3t, C2 e to the minus t minus 2 e to the minus t. Okay, so we wrote now those. Also, if you look at, I mean, you can, this matrix, the matrix you computed its determinant, so this is going to be then a fundamental matrix. So I mean, fundamental matrix is the matrix whose columns are solutions, which are linearly independent. Furthermore, if you, I mean, since they are going to be linearly independent, for each t, that means its determinant must be non-zero. And so if its determinant is non-zero, it's going to be invertible. So a fundamental matrix must be invertible. Just don't forget this. All right, now, but our problem was initial value problem. So what was the initial value? It says that at 0, we must get 1, 1 for each solution. So when you plug in 0, we must get 1 for the first solution and 1 for the second solution. I mean, like 1 for the first function we are looking for, which is x1, 1 for x2. So if you plug in 0 into the general solution, then we get C1. If you plug in 0, we get 1 here, 2, C2, 1, and minus 2. So if you look at this, is exactly this solving the following equation. So we have C1, C2, and so we have 1, 1, 2, minus 2 is equal to 1, 1. Okay, so this is what we need to do. Because if you read the above, we have C1 times 1 plus C2 times 1. That's your first equation. So we have 1, 1 as the coefficient. So C1 times 2, C2 times minus 2. This is what we get. But we know, I mean, this is the this matrix is already invertible. This is invertible because it must be invertible. How do we know that? Because it's exactly in the fundamental matrix you are plugging in 0. So in this matrix, you are plugging in 0. So it's going to be invertible, and actually we know its determinant, that's going to be minus 4. And what is then this solution? So C1, C2. Okay. And for a 2 by 2 matrix, we know the inverse. Inverse is 1 over determinant times, now 1 over determinant. So what is the determinant of this matrix here? That's negative 4. And then you multiply to find the inverse. You just switch the main diagonal entries, negative 2 and 1, and you negate the other diagonals. So minus 1, minus 2. And then when you multiply with 1, 1, you will be able to get C1 and C2. So let's do it. Okay, so let me just say, give a name maybe. So let's say this is the matrix K, and this product is K inverse. Okay. Okay. If you look at the product, so we get negative 3, and we have negative 1. So then we get 3 over 4, and we get 1 over 4. That's C1 is 3 over 4, and C2 is this. So then the solution we are looking for is equal to 3/4 times the first solution, which was e to the 3t to e to the 3t, and 1/4 times the second solution, which is e to the negative t minus 2 times e to the negative t. So if you write them, we have 3/4 e to the 3t plus 1/4 e to the minus t, 3/2 e to the 3t, and minus 1/2 e to the minus t, which are basically, this is your x1t, this is your x2t. That's what we got. Okay. Now we were able to get it. Now, so basically, I mean, it all reduces to finding the eigenvalues and eigenvectors of the corresponding coefficient matrix A here. But now, yes, we were able to do it, we were able to get it, but is it always possible? Of course not. I mean, of course not. So maybe let's write a note here. So given x prime a x, then we know that if you compute determinant of lambda to a minus lambda I is a nth degree polynomial. So then what are the possibilities for the roots of this polynomial? And so determinant a minus lambda I 0 gives us the following possibilities. All roots are real and distinct. So that means all roots here are eigenvalues. Okay, maybe just all eigenvalues are real and distinct. In this case, how many eigenvalues you have? You will, since it's an nth degree polynomial, you can have at most n eigenvalues because you are finding roots. It's an nth degree polynomial. We have at most n many distinct roots. So then, if all of them are distinct and real, then you will be able to get one eigenvector for each of them. So that means you have n many eigenvalues and one eigenvector for each of them. Automatically, you will be able to write one solution for each of them. So that this way you will get n many solutions. And so in this case, then what are we going to have? We will have lambda 1 till lambda n. Okay, and each eigenvalue, when you solve the system, it will give you an eigenvector, at least actually, in this case, also at most, then you will see this effect from linear algebra. So then here, we will be able to get the first solution, e to the lambda 1 t times c1, which is the eigenvector of, maybe let me just use the index above. This is the eigenvector of the eigenvalue lambda 1. So you will get another solution, e to the lambda 2t times c2, where c2 is an eigenvector of lambda 2. So, and you will have e to the lambda nt times cn. Okay, so this is this way. You will get n many solutions. How do you know they are linearly independent? So let's compute their Wronski. I wasn't putting t. So this is the determinant of e to the lambda 1t times c1. So basically there's a vector here, c1, and you multiply its components with e to the lambda 1t. So, and the last one is e to the lambda nt times cn. Okay. And effect from linear algebra, so if you multiply a column or a row with a constant, and the determinant is affected with that constant. It's the same amount. So, and this is equal to, and so that's the reason you can take all these coefficients out. So you will get e to the lambda 1t, e to the lambda 2t, e to the lambda nt times determinant of these vectors, c1, cn. And if you compute this determinant, so this is going to be, this part is just e to the lambda 1 plus lambda 2 lambda n times t, and which is never 0. And furthermore, this determinant is of the eigenvectors coming from different eigenvalues is also not 0 because they are linearly independent. Of course, I mean, I didn't prove this thing, but its proof is not very difficult. So if you have eigenvalues, if you have eigenvectors from different eigenvalues, then they cannot be linearly dependent. Okay, so then this determinant is never 0. As a result, you can use these solutions to write the general solution. Okay, and then second case, eigenvalues are let me maybe state in the following way, just so as the book does. So some eigenvalues are complex and even the last one, some eigenvalues are repeated. In the upcoming section, then you will see like the second case, some eigenvalues are complex, and you will see, I mean, they will come as conjugate pairs. So you will not be able to have one eigenvalue which is complex. If your coefficient matrix is real, its conjugate must also appear, and in the upcoming thing, so some eigenvalues are repeated. So for the complex eigenvalues, again, there is no problem. You will see you will be able to get n many linearly independent solutions, but the problem occurs when your eigenvalues are repeated. Because if the eigenvalues are repeated, then you need, for the same eigenvalue, you have to find linearly independent eigenvectors, which may not occur. So that way, I mean, from this method, if you want to write like the solutions, x is equal to e to lambda t times c, all the c's must be like linearly independent, then you may not be able to get enough solutions to write the general solution. So that's, in that case, you have to do something else, and you will see that later. Then let me finish it with a 3x3 example, but I will do it quickly because this video is a little bit longer than the usual ones. So I will do it quickly. So just to show you, like, repetition is not the problem. The problem is the number of linearly independent eigenvectors. So your eigenvalues may repeat, but if you, even in that case, you may still have enough eigenvectors. Okay. But this time I will be quick. You can check the details. Check my notes. Okay, so our system is the following. I'm writing the coefficient matrix: 1, 0, 1, 0, 2, 0, 1, 0, 1. Okay. Now, if you do determinant of a minus lambda I, which is going to be a determinant of 1 minus lambda 0, 1, 0, 2 minus lambda 0, 1, 0, 1 minus lambda. So we can expand over any, of course, and let's expand this determinant by using the second row, because we have 2 zeros and 1 non-zero term. And so then what do we get? We will get -1 to the power, if you look at the position of 2 minus lambda, so we have 2 minus lambda as our coefficient, then its position is 2, 2, so we have 2 plus 2 times the determinant of the 2 by 2 matrix, where you delete second row, second column. So which gives us 1 minus lambda 1, 1, 1 minus lambda. So from this, we get 2 minus lambda. If you do this determinant, we have 1 minus lambda square minus 1, and which will give us 2 minus lambda. And if you do this thing, so we will see, if you expand it, 1 minus 2 lambda plus lambda square minus 1, and which gives us 2 minus lambda. So if you do this, so ones are canceling, so we have lambda parentheses, so minus 2 lambda, let me write this first, lambda square. And if you do this, and we have minus lambda out, and 2 minus lambda square. Okay, so this is what we get. So the roots are 0 and 2, but 2 repeats twice. Okay, now let's find the eigen vectors. For lambda equal to 0, I'm going to solve a minus 0 times I, because c is equal to 0. And I will just directly do the row reduction. It's a homogeneous thing, so I'm not writing 0. for the augmented matrix to save space and time. So our matrix is 1, 0, 1, 0, 2, 0, 1, 0, 1, because I'm not subtracting anything from this. As you can see, like here, if I take the first row, multiply with minus, and add to the third row, then I will get 1, 0, 1, 0, 2, 0, 0, 0, 0. It's already in the row reduced echelon form. So this is my pivot, this is my pivot. And so here, third variable is free. So C3 is free. And so if you write your equations back again, this thing says that 2 C2 is 0, because, you know, remember, like we have a hidden 0 and 0 and 0 here. It's a homogeneous, whatever operation you do, they are always 0. We don't write them to save space and time. And first equation says C1 plus C3 is 0. So which tells us the following: C1, C2, and C3. So C3 is free. So free things are equal to themselves. So it's equal to itself. So from the second equation, we see that C2 is 0. And from the first equation, we see that C1 is equal to minus C3. And which says that if you take C3 out, minus 1, 0, 1. So out of this, we can write our first solution, e to the 0t times minus 1, 0, 1, which is exactly minus 1, 0, 1, a constant vectors. Now, lambda is equal to 2, so I need to solve a minus 2i, because c is equal to 0. This time, again, I'm subtracting 2 from diagonal entries, so I get minus 1, 0, 1, 0, 0, 0, 1, 0, minus 1. Again, I didn't write the 0 since it's homogeneous. If you do the following row reduction, take the first row and multiply with minus, I'm sorry, not anything. So just take the first row, add to the third row. And if you do this, we get minus 1, 0, 1, 0, 0, 0, 0, 0, 0, which tells us there is only one pivot, which is the corresponding to first. So here, C2 and C3 are free. So our equation, there's only one equation here, minus C1 plus C3 is equal to 0. Again, let me remind you, there is 0 here, 0 here, 0 here. There is 0 here, 0 here, 0 here. We never write them to save space and time. So then what do we get from this? C1, C2, and C3. Then we get the following. C3 is equal to itself because it's free. C2 is equal to itself because it's free. And as you can see, C1 is equal to C3. Because we are writing the things in terms of the free one. So if you take C2 parentheses, we see 0, 1, 0. If you take C3 parentheses, we see 1, 0, 1. Okay. So we have, now if you look at, we have two eigenvectors, not only them, their multiples are, so their linear combination. So basically, I mean, these are two eigenvectors which are linearly independent. Because how do you check linear independence for two? They're not multiple of each other. So I can use each of them to write my solutions. So I can write the second solution, which is going to be e to the 2t times 0, 1, 0. And I can write my third one, which is 1, 0, 1. So then I'm leaving the Wronskian check to you. So you can easily see that Wronskian is non-zero. So then our solution will be e to the 0t. General solution will be minus 1, 0, 1. C2 e to the 2t 0, 1, 0. C3 e to the 2t 1, 0, 1. So we were able to write 3 solutions, even repetition occurs. So repetition may occur for the eigenvalues. As long as you find enough eigenvectors to write solutions, then you will be able to write the general solution. Again, I'm leaving the Wronskian check to you here. Okay, so actually I can tell you what the Wronskian is going to be. Wronskian is up to constant. We know from Abel's theorem, Abel's formula, Abel was saying that Wronskian of these kind of things will be up to constant, so C times e to the integral of the diagonal entries. In our matrix, if you look at the diagonal here is 1, 2, and 1. So this is diagonal. When you add them up and integrate, this is what the, so 1, 2, 1 dt. Oops. So C times e to the 40. And then you can easily check this. C won't be 0, so they are going to be linearly independent for all t. Okay, so now in this section we learned a method to write the general solution. Basically, for constant coefficient case, it reduces to finding the eigenvalues and eigenvectors. As long as you have enough eigenvectors, then linearly dependent enough eigenvectors, then you can write the general solution. So in the upcoming lecture, you will see the complex case, and following that, you will see the repetition case, where you need to do something more to write some needed solutions. Okay. Now I'm finishing the lecture. Have a good day. Stay safe and healthy.